Today we're going to continue talking about exponential growth. So yesterday we explored exponential growth for the very first time and saw what those graphs look like. Now today we want to talk about where might this actually be used. What could exponential growth be good for? So we will be looking at word problems. In these problems we're going to be using the formula here, which is our general model for exponential growth. So y is some amount that we're trying to measure. It says is equal to 1 plus our rate, which is a rate of growth, and then to the power of t. And there should also be an a in there, right in front of it. I don't know why, but I think it's there on yours, and for some reason it's just not on mine, where a is our initial amount, so however much we start out with. So we're going to take however much we start out with and multiply it by 1 plus our rate. Okay? Now yesterday we talked about how the bigger that base is, the faster the growth we're going to see. So if our rate is 100% growth, then we would have a base of 2. We would be doubling each time period when you have 100% growth. You're doubling each time period. We can also have percents that are larger than 100, which seems maybe a little bit counterintuitive, but something can grow by 200% in a year, which then if we would plug like a 2 in for our rate for 200%, we would be tripling our value each time period then. So that rate is going to be our growth rate. The bigger the growth rate is, the faster we're going to see this thing take a turn, and the sharper of the turn that's going to be. You don't need to memorize this formula, but using it over and over, you might end up catching it along the way, but you don't have to memorize it. In January 1993, there were about 1,313,000 internet hosts. During the next 5 years, the number of internet hosts increased by about 100% each year. Write a model giving the number h in millions of hosts t years after 1993. About how many hosts were there in 1996? Okay, so we're going to start with our general model, which is y equals a times 1 plus r to the t. In this problem it says write a model giving the number of hosts h. So we're going to use the letter h instead of y just because sometimes in a word problem it's nice to use letters that actually represent what you're talking about instead of always using x's and y's. So here we're using the letter h to represent how many hosts we have. A is our initial amount. So how many did we start with? 1,313,000, and it says in millions in the problem, so we're going to change that to 1.313, so we don't have to deal with as many zeros when we're doing our calculations, times 1 plus our rate is 100%. Always turn it to a decimal when putting into the problem, though. Do not leave it as 100. Your graphs will be insane. Okay? Always turn your rate to a decimal, so 100% as a decimal is just 1. And then to the power of t for time. So that gives us a model of 1.313 times 2 to the power of t. There's another part of this that says about how many hosts were there in 1996. First, when it asks for a model, make sure you still have 2 variables in there. Okay, a model is an equation that tells us the relationship between 2 variables. So we want to make sure that we don't actually plug anything in for h or for t yet when we're talking about our model. But now the question goes on and says how many hosts were there in 1996. So now we want to plug something in for t. What do we want to plug in for t? 3. We want to plug 3 in. Why do we want to plug 3 in?
There's 3 years moving 1993.
Because it's 3 years past the beginning. So we're starting our beginning at 1993, and this is 3 years past the beginning. Okay, so t is the amount of time that has passed since the problem started. Okay, the problem started in 1993. We're talking about 1996. 3 years have passed. So we plug that in. We just plug that right into the calculator to get an approximation on that. And that is about 10.5. So there's about 10.5 million internet hosts in 1996. Fun story about this. I remember when I was fairly young, junior high-ish, it should have been early 90s, my father coming home from work, and he's a professor at university, and he's like, they have this thing called the internet now. It is so stupid. It's not going to go anywhere. And he was just like all angry about this thing called the internet that they had at work now. And Like, just looking back, how ridiculous that was. In his defense, it was ridiculous when it started because there were no search engines. So you had to know where you were going, and the addresses were like really long. So unless somebody gave you this ridiculously long address, there was no way to ever find anything you needed. So it did start out as a very stupid thing, but it's grown into something that he never foresaw. And I love it when my father's wrong about things because he's right about everything. So on the rare occasions he's wrong about something, I have to hold on to those. So it has grown insanely. I don't know if it's still continuing to double each year, but when it started, it had some very fast growth rate and we doubled each year. We want to graph the model showing how quickly this growth takes place. That's not what I wanted to do. Okay. So when we graph these today, yesterday on our XY axis, we used all 4 quadrants. Today in our problem, since we're going to be talking about practical applications, we're just going to be plotting them into the first quadrant because we're not going to care about negative time, and there's no such thing as negative internet hosts. Right? So while we're working with our problems today, we're just going to be working the first quadrant region. So you can draw your graphs accordingly, and that gives you more room to plot what we need. We're going to make some charts like we did yesterday. So instead of calling it X and Y, I'm going to call it T and H, since those were the letters in our equation. Once again, that equation was 1.313 times 2 to the T. So I'm going to pick some T values to plug in. That would be easy. I'm not going to plug in -1 because we're not talking about negative today, but I'll plug in 0. 0 is an easy thing to plug in because it always just gives you the front number. We already plugged in 3, so we might as well use that piece of information that we have, that was about 10.5. And then I'm going to use the part C of the question as a little bit of a help to me here as well. In part C of the question, it says, use the graph to estimate the year when there were 30 million hosts. So what I want to do is try to pick some T values by kind of guess and check that are going to get me close to 30 million. So I would try maybe 5. If I plug 5 in, I get 42. So I went a little bit too far, so I guess maybe I should have just gone 4. If I go to 4, I get 21. All right, so it's got to be somewhere between there then. Okay, so about 4.5 years looks like when we had 30 million, and that helps us answer part C. Then we're going to want to go ahead and plot these out. I'm going to let each one on my x-axis be time in years, and I'm just going to count by 1 years along here. And then our y-axis is going to be the hosts in millions. And if I need to get up to 42, I probably don't want to be counting by 1s. Maybe I'll count by like 3s. And then we'll go ahead and plot our points. So at time 0, I had 1.313, so that's about 1/3 of the way up to 3. Year 1, I didn't do, so we don't need to plot that point. I didn't do year 2, that's fine. You don't have to do every single point. Year 5, or year 3, I've got 10.5. Year 4, I've got 21. And year 5, I've got 42. And then connect the dots. We don't need the arrow pointing out towards the negative side because we're not going back in time here, but we should have the arrow pointing on up. All right, and then our answer to the last question we already kind of talked about, but estimate when we had 30 million hosts. So I'm going to take this 30 million value and say about when does that happen? And it's a little bit after 4, kind of between the 4th and 5th year. Okay. So if time started in 1993, then what year would that be in?
1997.
1997. Sometime in 1997 it happened. 4 and a little bit after our start. So sometime in the year 1997, there was 30 million internet hosts. Okay.
Wait, how did you get 97?
We found that on the graph it was kind of between 4 and 5 years, and since time started in 1993, we're looking at about 4 and a little bit years afterwards. Okay, so and we want to pay attention to our question there because it didn't say how many years later. It did say estimate the year. So answering it with about 4.5 wouldn't be an appropriate answer. We want to actually make that into a year of 1997. Right? One other thing to watch on this is this says during the next 5 years, the number of hosts, blah, blah, blah. Okay, during the next 5 years. That means this model is really only valid for a short amount of time, which is often true with something new. That in the beginning we may see some rapid growth on this, but it's going to have to slow down at some point. So then we would need a different model. So that means you would not want to use this model to estimate how many internet hosts there are today, for example. Okay, because it's probably not still doubling every year. All right, so make sure you pay attention to kind of the parameters on that and how long this function is good for. It's only good for 5 years of estimation in this particular problem. In 1990, the cost of tuition at a state university was $4,300. During the next 8 years, tuition rose 4% each year. Write a model that gives tuition Y in dollars T years after 1990. So our model is A times 1 plus rate to the power of time. What's A? 4,300. What's our rate?
4%.
4%, which we're going to say is 0.04. Always change to a decimal when plugging your rate in. Power of t. 4,300 times 1.04 to the power of t. Okay. That's all that question asked us to do, was just to write a model. It didn't ask us to find the tuition at any particular time. Then we're going to want to graph it. And in that graph, we're going to want to aim for looking of a value of about 6,000 to be able to answer the third part of this question. Okay, so when we're picking our time values, we're going to want to pick things that help us find an answer around 6,000. Yesterday we talked about that base value, and the bigger that base value is, the more drastic of a change it's going to make in our graph. We said the closer to 1, if it's actually 1, you're just going to get a straight line. 1.04 is really close to just being 1. This thing's going to look pretty straight line. It's not going to look like as much of an exponential curve as we've seen in other problems because that rate is so small. So in making the chart, 0 is always easy to plug in because you just get the front number. And then we grab a calculator and plug in whatever numbers we want. So maybe I'll plug in 2. If I plug in 2, I get 4,650. I'm trying to keep like 6,000 as a goal in mind since that's what the third part of the question asked for. So that didn't really help out very much. So maybe I'll jump up to 7. 5,659. Okay, so I'm not quite there yet. Maybe I'll jump up to about 10. 6,365. I passed by it, so maybe I'll go back and plug in 9. $6,120. So I'll go back and plug in 8. Okay. These all have decimals on them, but I'm just rounding them off because it doesn't really matter. We're going to be putting it into a graph anyway, right? So you don't have to have like perfect answers here because you're not going to be able to plot them perfectly. So then when we go to plot this, I'm going to count time in years. And I'm going to count dollars on our y-axis. And if I have to get up to 6,000, I'm maybe going to count by like 500s. So then when I plot my points, I've got 0, 4,300, got 2, 46, 7 up to 56. 8 up to 58, 9 just passes by the 6,000, and 10 even more so. I kind of connect these in, and it looks pretty straight line. We're not seeing a really sharp turn because it was such a small growth rate. Okay, so you don't always see a super sharp turn in an exponential function. That happens as our base gets larger, and when we have a small base, you shouldn't expect to see a sharp turn. And then to answer the third question, when did this thing hit the 6,000 mark? We can kind of see either from the graph or from our chart that it was somewhere kind of between year 8 and year 9. So since this started in 1990, then we would say in 1999. Sometime 1998, 1999. They usually only change tuition rates like at a semester or even at a year, so we'll kind of round up on that. All right. Questions? The next application we're going to look at is money, which students always like to think about math as having a purpose for thinking about money. And we're going to talk about compound interest. Compound interest is an awesome thing. Compound interest, you put your money in the bank and you let it sit there. And what happens is after a while they give you some money. That's called interest. So the bank gives you some money, adds it onto the money that you have, and then the next time that they go to figure out your interest, they figure not only on the money that you put in there, but also on the money they gave you. So now they're giving you money on the money they already gave you just for letting it sit there. It's a beautiful thing. Your money can start growing very fast after a while, but it does take a while. So you can't put money in the bank and then all of a sudden just like expect it to explode. Okay? That's the nature of an exponential function, is it stays pretty flat for a while, but then once it takes its turn, it starts growing very rapidly. So banks can choose how often they want to give you that interest, and that's called our compounding period. So they could give you interest once a year, and just at the end of the calendar year, they give you however much money you earned in interest, and that's it. And then the next year, they'll calculate your interest again. They could do it each month. They could do it each quarter. They could do it each day. They can decide. In reality, what most of them do is something called continuous compounding, which we'll talk about later in the chapter, but we have to learn something else before we can apply that formula. Our formula here is pretty messy. You do not need to memorize this, you just need to understand it so that you can use it and plug stuff into the right places here. So A is the amount of money that we have. P is our principal, which is a financial term for how much money you start with. Okay, so your principal is your initial investment into your bank account. Then our rate is our percent rate that we're gaining interest here, and we're going to divide that by the number of times they compounded a year. Because if they tell you that they're giving you 6% interest, but that they're compounding it 4 times a year, they don't actually give you 6% every time they compound it. They give you 6% over the course of the year, which would then need to be divided up into each compound period. So we take the rate and divide it up by the number of times they're giving us interest to the power of compound times years, however long we're going to let it sit there. The longer we let it sit there, the better it's going to be. Okay? So this formula is pretty disastrous, but you don't need to memorize it. We just need to know where to plug stuff in. So, write that formula out again. Amount is principal 1 plus rate over compound to the compound times time. You deposit $1,000. That's our principal. Into an account that pays 8% annual interest. That's our R. Find the balance after 1 year. That's our T. If the interest is compounded with a given frequency, and then we have 3 different questions here. So first, for annually, our compounding is going to be 1. They're just going to give it to you on December 31st and then not again until the next year.
What is that?
N is the number of times they compound it in a year. So if they're just giving it to us annually, they're just giving it to us once a year. So then if we're going to do amount 1,000, 1 plus, interest rate, again, always turn it into a decimal, 0.08, divided by the compounds, which is just 1, the power of 1 times 1. Now with this formula and a lot of 1s in it, it simplifies down pretty nicely as far as being able to plug it in your calculator easily. So we get 1.08 just to the first there, which means we get 10,080. So they're going to give you $80 for just letting your money sit there for a year. It's pretty nice. And then the next year when they go to figure out your interest, they're not going to figure out how much interest to give you just on the 1,000 that you put in. They're going to figure interest on the whole thing. And that's why this exponential growth happens, is because it's going to start building off of itself, and that interest is going to be growing as well. When we go quarterly, we're going to get our interest 4 times a year. The formula is going to be the same except for we're going to have to divide by 4, and we're going to have a power of 4. Now this is where it gets a little bit trickier to start plugging things into the calculator. What I would suggest doing is plugging it in pieces and not trying to plug it all in at once. You can plug it all in at once. You need a lot of parentheses and you have to be very careful with what you're doing. So what I would suggest doing is 1 plus 0.08 divided by 4 and let your calculator tell you what that is. Okay, so we do inside the parentheses first. Then go to the power of, and then in parentheses, 4 times 1. Now since it's just 1, it doesn't really matter. But if we were leaving our money in there for, say, 3 years and we needed to do 4 times 3, those parentheses would matter. Okay, because we want all of that to be our exponent. And hit enter. And then multiply that by the 1,000 that's out front. And hit enter to get our final answer. So you can type it all in at one piece. You need a lot of parentheses though, and often things go wrong for students who try that. So when we do that, I end up with a final answer of $1,082.43. So if they give me my interest 4 times a year instead of just once a year, I end up with an extra $2.43, which is nice, but that won't even buy me Starbucks, so it's not like great. But the more often they compound, the better it is for you, okay? Because when they compound, they're adding money to the interest. So if they put interest in more often and add money to that interest, your money's going to grow more quickly. So the more often they compound, the better it's going to be for you. In the short run, it doesn't make a huge difference. In the long run, it can make a very large difference. Okay. Always round your pennies down, though. They're nice enough to give you interest. They are not nice enough to round up. So always round your pennies down, no matter what that third decimal place is. Just always round your pennies down. If we go daily, our N is going to be 365. And again, I would suggest plugging it in 3 pieces, and I'll go ahead and just show you what that looks like on the calculator. Okay, so I would do what's inside the parentheses first. So 1 plus 0.08 divided by 365 and hit enter. And then I'm going to go to the power of, and it'll automatically reuse your answer, 365 times 1. And again, it's times 1, so it doesn't really matter in this problem. But if it was something else, if we were leaving our money in for more years, then it would matter that those parentheses were there. Hit enter, and then I multiply that by the principal, how much money I put in the bank, which was $1,000 in this problem. So I get $1,083.27. Again, always round down. They're nice enough to give you interest, but not nice enough to round up. So always round your penny down there. So then I get an extra $3.27 when they compound it daily instead of just giving me my money once a year. Still not a huge difference, but that difference will kind of explode over time. If we left our money in the bank longer, it would make a much larger difference over time. And hey, I'm not going to complain that it's only like $3.27 difference when really they just gave me $83.27 for doing nothing, right? For just letting my money sit there. I didn't have to work for it. It just sat there and I earned $83.27. So compound interest is a really nice thing. We have one more example of this, but I don't necessarily feel the need to run through it because it's the same thing. We're just going to plug stuff in. But I do want to talk about the other time periods and just make sure you're on with what those are going to be. So we already talked about annually. Semi-annually would be, N is what? 2, twice a year. Semi means half of a year, so it means they're going to do it twice the year then. Quarterly would be 4 times a year. Monthly would be 12 times a year. If they do daily, always do 365. Yeah, maybe it's a leap year, whatever, but always just do 365 if we're talking about daily. And your homework is from 8.1 again, so make sure you're looking at the right section there. We're still in section 8.1 tonight.